we present TRASS, time reversal as self-supervision. In this work, our objective is to tackle challenging vision-motor tasks without strong reliance on human supervision. We propose unsolving the task as a cheap but effective source of supervision towards solving the task. Learning vision-motor policies for complex manipulation tasks remains an open and challenging problem. Prior work has tried to tackle these challenges of vision-motor learning from a number of angles. One approach to vision-motor learning is in reinforcement learning with human-provided rewards. While this has been successful in a number of tasks, it can take significant human reward engineering even for just a single task. Another approach is learning from demonstration, where the robot imitates a human demonstrator. While this is an effective way to learn challenging tasks, collecting a large set of demonstrations across a diverse set of environments can be very expensive. To mitigate some of these challenges, self-supervised reinforcement learning aims to learn exclusively from data which the agent can collect by itself, without a human in the loop to provide rewards. However, as a result of not having supervision, much of the collected data is not relevant to the downstream tasks. In this work, we ask the question, are there other forms of supervision an autonomous agent can leverage? Critically, we'd like this supervision to be scalable and as a result self-supervised and not depend on any task-specific rewards. Additionally, we'd like the data we collect with this method to be useful for downstream task completion. Our key insight is that for many tasks, unsolving the task is significantly easier than solving the task. Consider, for example, the task of putting together a jigsaw puzzle. Breaking apart a complete puzzle is substantially easier than putting together a puzzle from scratch. And furthermore, breaking apart the completed puzzle can provide valuable information on how to complete the puzzle while not requiring any human supervision. More formally, we assume the following problem setting. We assume a finite horizon Markov decision process defined by a state space S. There are a subset of states which are goal states SG, and the reward is defined as 1 when transitioning into a goal state and 0 otherwise. We make 3 specific assumptions in this work. First, that during training we can reset to some subset of goal states SG prime. These goal states are disjoint from the ones seen during testing, and no information is provided about how to reach these goals. For example, in the case of the jigsaw puzzle, this simply amounts to being able to provide a robot with a completed puzzle. Second, we assume that there's a non-zero probability of reaching any state in the state space from a goal state. This simply ensures that there are no irreversible transformations, such as breaking an object, and holds in most manipulation tasks. Lastly, we assume that if a state can transition from a state Si to state Sj, then there exists some sequence of actions A star which can transition from Sj to Si. This guarantees that any sequence of states can be traversed in reverse. Note, this does not assume the reversibility of actions, simply that some action can traverse the sequence in reverse. As a result of these assumptions, there are some settings where TRASS can be applied and some where it cannot, which we discuss at the end of the video. Now we concretely describe our method. First, the agent resets to a completed task state S0. The agent then explores randomly, unsolving the task, collecting a sequence of states S0 to St. The agent then reverses this trajectory and trains the time reversal model to predict this reverse trajectory. Specifically, given St, the time reversal model is trained to predict St-1, then St-2, and so forth, all the way to S0. At test time, the agent receives an unseen state. The time reversal model will then predict a sequence of states that lead to a completed task. The agent can then execute control using the predicted states as cost. Specifically, a policy pi takes the current state as well as the predicted sequence of states leading to a completed task and uses that to output an action. Now we will examine each of these components of TRASS in detail. We will begin by describing the experimental domain and data collection. We tackle the problem of Tetris block mating. Specifically, the task is to mate 2 parts into a 3x3 square configuration. Note, this configuration is pose invariant, and thus for an initial state, there are many possible goal states. The agent's observations are uncalibrated RGB images, as shown on the right, and the action space consists of a single push start and end location. For data collection, we leverage simulation with domain randomization. We then transfer the models trained on simulated data directly to the real robot. Simulation is particularly useful for TRASS because it enables us to reset directly to goal states. From there, we explore randomly, collecting the data for the time reversal model. For the forward dynamics model, we collect data by initializing to random scenes and taking random actions in the environment. We now go over TRASS reversal and training. Since we are in the visual domain, both the time reversal model and forward dynamics models are video prediction models. Specifically, we use SV2P, a stochastic video prediction framework shown on the upper right. The time reversal model takes as input the first frame of the reverse sequence and predicts the sequence of states leading to the goal, as shown on the slide. The forward dynamics takes a single state and an action and predicts the next state, as shown on the bottom right of the slide, where the green arrow indicates the action. We now overview how TRASS is applied at test time. First, the agent is initialized to an unseen state. The time reversal model then predicts the sequence of states that lead to task completion from that state. This sequence of states is then used as a cost for a sampling-based planner. Specifically, the planner samples actions, feeds them through the forward dynamics models to get predicted outcomes, and computes the cost of those actions based on their difference to the predicted trajectory. This is used to select actions, which are then applied in the environment. This process repeats until task completion or up to a fixed number of time steps. TRASS solves the problem of block pair mating on a physical robot from raw RGB input. Here we demonstrate a KUKA robot solving the block pair mating problem on a flat tabletop. TRASS is able to successfully mate the block pairs with a 75% success rate and generalizes to unseen block pairs. In simulation, we evaluate our method on a number of problem settings, including seen blocks initialized far away, and unseen blocks. First, we compare to using shaped rewards, specifically the convex hull of the blocks, and find that TRM significantly outperforms shaped rewards, even though it uses less supervision. Next, we compare the performance of TRM to using the ground truth goal image and find that it achieves comparable performance. Lastly, we conclude by discussing when TRASS is effective. Based on the assumptions listed earlier, there are certain problem settings where TRASS can be applied, and some where it cannot. The primary setting where TRASS is not effective is when the gripper is in the state and the gripper object dynamics are irreversible. Consider a video of a gripper holding up an object and then releasing it. The reverse video would show the object magically floating up into the air into the gripper. This is not a feasible sequence of states and thus violates assumption 3. However, in low-dimensional settings, this can be addressed by removing the gripper from the state, and in high-dimensional settings, a high-level action space can be used to circumvent this problem. Additionally, irreversible object deformations, like cracking an egg or welding an object, violate assumptions 2 and 3, and thus TRASS cannot be applied. TRASS can be applied in 2D or 3D assembly problems. For example, in the block stacking or object mating tasks, trajectories of disassembly can inform how objects should be assembled. In the majority of tabletop or desk manipulation tasks, time reverse trajectories of unsolving the task can inform how to solve the task. For example, closing a drawer informs how to open it. Similarly, in household manipulation tasks, like setting up a dining table, unsetting the table can inform how to set the table. Additionally, in all of the above settings, the process of unsolving the task can be substantially easier than solving the original task. The key takeaways are, TRASS enables learning to solve tasks by unsolving them. Time reversal provides a cheap but effective source of supervision, and TRASS can be applied to a number of challenging visuomotor tasks.